Isaac Newton was the first scientist to analyze light. He took a prism like this, put a beam of white light through it, and to his amazement, all the colors of the rainbow came out. He discovered that white light is actually a mix of all the different colors. Nowadays, we have something called a diffraction grating that works very much like a prism, but in some ways is more convenient. All large telescopes, the Hubble Space Telescope, have diffraction gratings. That's an instrument called a spectrograph, and it breaks light into its component colors and then images it so that astronomers can study the light. As a matter of fact, I was responsible for one of the spectrographs on the Hubble Space Telescope. So let's take a diffraction grating, and we'll use a beam of light formed by an old overhead projector, and we'll put the diffraction grating into the beam and see what we can analyze in the light. Two Germans, Kirchhoff and Bunsen, were the first to experiment in the laboratory and figure out the properties of light. Bunsen you may have heard of. He got his name on, you guessed it, the Bunsen burner. Kirchhoff you may not have heard of, but he got his name on the laws that describe the behavior of light. Kirchhoff's first law is that the spectrum of a hot solid object, like the filament of this lamp, or a hot, very dense gas, like the body of the sun, produces a continuous spectrum. If you take a look at the continuous spectrum, you can see that it consists of all the colors of the rainbow without any breaks. Let's experiment with an ordinary light bulb to see how the properties of the emitted light depend on the properties of the source. If I turn down the energy going into the light bulb, it looks like this. If I increase the energy going into the bulb, it looks like this. What do you notice changes from the light emitted as we change the amount of energy coming from the bulb? Shall I do that again? Relatively little energy, then more, then more. What color would this object look to your eye? That's right, bluish white. It's a mix of all the different colors, but with a little bit more of the blue and violet, and so it looks bluish white. You can also get a sense of how much more precise it is to graph a spectrum than to just look at it with your eye, or to use a spectroscope to show you how much of each different color is present. We can make a plot or a graph that shows how much energy comes out at the different wavelengths or colors of light. Now first take a look at this graph and you'll see that all the different colors of visible light are there, from red to violet, but even though you can't see it, there's also ultraviolet and there's infrared, and we can plot those. So in this applet, I can adjust the temperature of the source of the light, and I'd like you to observe carefully what happens when I change that temperature. For instance, if I raise the temperature a bit, the graph goes way, way up. So hot objects emit much, much more light than cool objects. And this is very accurate. So this is 7,000 degrees approximately. Let's lower the temperature. Now that's still pretty hot, right? 3,000 degrees. But let's go lower and lower, and there's less energy, so let's magnify the graph so we can see it. And what do you notice about the color of the light when the temperature is much less? Sure, it's less intense, but it's also shifted in wavelength. And as a matter of fact, at 2,500 degrees, there's more energy coming out in the infrared than there is in the visible. Well, let's look at the sun. We better make the plot go down because as I raise the temperature, more and more and more energy is coming out. Let's go up to about a little under 6,000 degrees. And that's roughly the temperature of our sun. So what energy is coming out of the sun? A lot of visual light, some red, yellow, and all the colors, of course. And when you have all the different colors, as we saw that Isaac Newton discovered, you get white light. And the sun basically looks white. If you were talking about a star that was hotter than the sun, notice that the balance of the colors has shifted. And there's a lot more of the blue and violet coming out. And so the hottest stars look bluish white. On the other hand, if you go to a relatively cool star, that would be about 4,000 degrees as stars go. There's a lot more red light, and so a star like Betelgeuse in Orion looks orange. The red giant stars we'll be talking about are low temperature stars, and that's why they look orange or red giants. Now, it is possible for a star to put out lots of energy even when it's cool if it's a very, very big star. But in the case of our sun, at a temperature of just under 6,000 degrees, there's a balance among all the visible colors, but there's also a lot of infrared. And just for fun, let's lower the temperature way down to the temperature of U. So people most of the time are at about room temperature. On the absolute scale, the Kelvin scale, room temperature is about 300 degrees. And so here's you. If you could take a look at yourself, you are emitting energy right now while you're taking this class. It's not visible light energy, it's entirely infrared. And we'll play with an infrared camera and point it towards a few people, and you'll see that we emit just like stars do, but we're such a low temperature, our emission is in the infrared, and the sun's over here. So hotter means brighter and bluer. Notice that the wavelength of the maximum intensity is inversely proportional to the temperature. So as you make something hotter, the wavelengths get shorter or bluer. And the total energy goes way up as the temperature rises. It's actually proportional to temperature to the 4th power. So if you make something twice as hot, the energy coming out is 2 times 2 times 2 times 2, 4 factors of 2, or 16 times as much. And that applies to stars like the sun.